that it would evenly distribute over the whole thing. All right, so now, so I got a certain amount of charge on there, evenly spaced if you wish, but it really is not crucial. And now I put a little cut right there, somehow with some non-conducting blade. Will I still have the same amount of charge that is stored?
So you cut the wires and you put them, place them.
Yeah, so the wires, so I split the wire so that now one of the wires goes to the sort of the upper half, the other one goes to the lower half.
And then you place one, have like a little nip in between them.
Yeah, so that these are down to, instead of having a solid plate, you now have two smaller plates.
There, you're gonna have a little.
Assume that the cut did not lose any metal in the cut.
Yeah, assuming your area stays the same, you should have the same amount of charge, right?
That's what I was going for right there. Right, Devon, it looked like you were trying to bring too much realism in at this point.
I thought because you had to cut it, something's you're gonna see something.
Yeah.
Yeah.
And this is the magical board cut. Yeah. If I have the same amount of area, it's just that the area of each one is different. So I can treat this as two capacitors though. I've got my upper capacitor, which is basically half the area the previous one did. And then I've got the bottom one, if I indeed cut these in half, which is half the area previously. So I basically have two capacitors that are half the capacitance of what I started with. So if this started as a 10 farad capacitor, I now basically created two 5 farad capacitors. If we think about charge flow here, I have charges that are flowing from this side right here, electrons more specifically flowing from the negative side, flowing up here, some going up, some going down. So one goes up, it chases one away from the upper plate, one comes down, chases the electron from the lower plate. And so we basically have a current flow here where current is flowing. If I ignore the gap in the middle, I have current flowing. I have charge flowing. I'll get to why I'm hesitating later. So I have charges flowing basically here, it splits, and then it comes back again. So whatever charge leaves the negative side will be the same amount of charge coming in the positive side. If ever I have current that can split, now I probably should do this now then. And I apologize if I've done this before. I got the two classes which are basically roughly the same spot, the 152 and 252, roughly in the same spot. And so I'm forgetting which group I've said what to what. So I'm just trusting that if I act like I've already told you something, you'll let me know that you haven't. Or what sometimes happens is one person doesn't remember it, but everyone else does. When Ben Franklin was setting up the convention, he said, imagine currents flow downhill. If you look at a river, it goes downhill. So I got a positive and negative plate here. So you picture this is the high potential, this is the low potential, and so current will flow from the high to low. He pictured a fluid, some sort of this positive, and it was pictured as a positive fluid that was flowing until they realized later that electrons existed in the 1800s sometime. It was J.J. Thomson who figured it out. So once they realized it's the electrons flowing, and the electrons were flowing in the opposite direction, they said, yeah, great, we're not going to change our convention. The current still flows from the positive to the negative, even though from, at least in classical physics, it's the electrons flowing in the other direction. Some textbooks will just call it electron current, and traditional current, I tend to just call it electron flow and current. So we have a current that basically is flowing from the positive side, gets to this junction, and then will split. So this right here, where there's a choice of paths, is a junction. if the current sort of comes back together at a junction on the other side of some component. So if I have current that splits and then comes back together, we have a parallel construction here. These would be capacitors in parallel. With the less curved lines, more traditionally, it would be written as something along like this. These are capacitors that are in parallel, so this would have some capacitance C1, this is some capacitance C2. The voltage drop across both of them is the same, because again, if I started in some point and end up back in that point, there's no potential difference total. So if I start here, go across my battery, I'm gaining whatever the voltage of the battery is, 12 volts, given my example right there. Come up here, and this time I go down this path, and I cross, and then back to where I started. If I gain 12 here, I have to lose 12 going across the capacitor in the direction that I just went. Or if I went across the top one, I would have lost 12 volts across this. So the potential difference between the two plates is still the same as the source down here in this particular situation.
So, no, not to interrupt, but are we gonna be given problems that the capacitors are different?
Yes.
In parallel?
Yeah. So one of the features of capacitors are anything's in parallel, objects in parallel have the same potential difference. I guess properly, the same magnet, same absolute value of potential difference, because it really does matter which way you're going across them. I guess if I call this point A and this point B, then the potential from A to B is the same. From some junction to another junction. And then the equivalent capacitance, well, we'll just reverse what we did over there. Since this 10 farads kept the same charge and had the same voltage, splits into 2 5s. If I start with 2 5s, I can get to the 10, or the equivalent capacitance. So if I wanted to take those two out and put in a single capacitor, I just add up the capacitances, however many I have. So if that's a 3 farad capacitor, that's a 2 farad capacitor. What is the equivalent capacitance?
5 farads.
Yeah. So they're in parallel because I have a junction on one side, a junction on the other side. There's nothing between them and those junctions. And so they are in parallel. And so my equivalent capacitance in this case, 5 farads. Questions to hear? Alright, so this I have a capacitor here. And then I make the distance between them larger. What happens to my capacitance?
It goes down.
Okay. So by putting bigger gap between them, I lose capacitance. So C goes down. Now what I'm gonna do is I'm gonna stick basically something in between it, create two capacitors. I'm not changing any of the charge that's stored, so if this had negative Q on it and that had Q on it, that would still have negative Q on it, and then when I put this here, it's just gonna chase electrons off of this plate over to this plate. And so this will have Q, and this will be negative Q and Q. So in essence, what I've done is just by having capacitors set up like that, that's similar to all I've done is I've just increased the distance between the capacitors. So this is known as series capacitors, or capacitors in series. And if you think about it in terms of current flow, if I have current that is flowing across here, there's no junction. Basically, what identifies series is that there's no junction in between. From a sort of more of a sweeping point of view, is that Q will be the same plus or minus Q, depending on the plate. Plus or minus Q, same for all in series. Or what will become more important, the current, this is current. Same across. Series. Not necessarily getting the same current in parallel, but you have the same voltage in parallel. Here you'll have the same current, which translates also to the same charge. So let's derive this a little bit more than just the conceptual thing that I did there. So I've got two capacitors in series. Well, C1 and C2. And I want to find the equivalent capacitance. In other words, what's the overall capacitance that I have here? If I have this hooked to, let's hook it to a battery. So whatever the voltage of my battery is, the voltage of my power supply, that's got to be equal to the voltage of capacitor 1 plus the voltage of capacitor 2. So whatever I gain going across my battery, I'm going to lose some going across capacitor 1, lose some more going across capacitor 2. So I get back to 0. I could have also written this as the change in the potential across the power supply minus the change in potential across 1, minus the change in potential across, that should be a 2 there. 2 is equal to 0. I could have also written it with all plus signs and just know that 2 of them are negative. So looking at this form right here, my equivalent capacitance, if I just had the single capacitor, well, I know C is equal to Q over delta V, so delta V is equal to Q over C. So this would be Q over the equivalent capacitance is equal to Q1 over capacitance 1 plus Q2 over capacitance 2. But as discussed, all those Q's are the same. So I can just divide them out. So I get 1 over the equivalent capacitance is equal to 1 over C1 plus 1 over C2 plus however many I have in series. So if I have a 3 farad capacitor and a 4 farad capacitor, what is the equivalent capacitance?
12/7.
I got 1/c equivalent is equal to 1/3 plus 1/4, which is 4/12 plus 3/12, 7/12. And so my equivalent capacitance, 12/7. I do want to comment on the fraction versus decimal form. I know that there have been some math instructors here in the past that have always said, hey, if you're working with fractions, stick with fractions because this is more accurate than if you round it off with a calculator. And I understand that. However, because this is physics, yeah, I say a 3 farad capacitor, but in reality, if I had a 3 farad capacitor, probably not 3 exactly anyway. This is probably rounded off, or this is ideal. So in science, all the numbers are rounded to begin with, so this is not necessarily more accurate than if we'd just been using decimals to begin with. So, but if you're a fan of fractions, stick with fractions.
And then on that, I know on that master set, it said something about not using fractions.
Yeah, one of the issues with fractions, if you're dealing with really large numbers, then it just takes an extra moment for me to go, all right, let's see, so if I did it with fractions, here it is reduced, and someone comes up with, you know, like 1,000 over 214. I'm going, all right, let's see, yeah, I guess I can divide that out, yeah, okay, that's the same thing. Or let me pull out a calculator and do the division and see what I get. It's just easier to do if everybody does decimals.
Gotcha.
But it's not wrong to keep it in fractions unless I specifically say use decimals. All right. So now, what is the equivalent capacitance? I should grab my calculator. You have your calculator with you, but wish to play along? There you go. Yeah, hopefully I'll remember tomorrow to actually get extra AAA batteries for such situations. All right, so I assume you have an answer?
I think so.
Yep. We have the same answer, so.
Well, that's good.
Okay. And then the reciprocal of that.
Oh,
Probably the most common mistake. Right, so I think I saw yours, didn't I? Oh, yeah, I saw yours. Stop filming. No. The three and two are in parallel. 4 is not in series with 3, 4 is not in series with 2. In order for things to be in series, basically there's no junction in between them, but I have a junction between 4 and 2 and a junction between 4 and 3. So I can't add them straight up. I have to figure out what I can do. Well, I got a junction here, so I got parallel. So I add them in parallel, and this becomes a 4 and a 5. And now I've got a series. So 1/4 plus 1/5 is 9/20. And then take the reciprocal, that's 1 over the equivalent. So equivalent capacitance, 20 nines. Farads, or 2.2 repeating.
So let's do the series first, and then do the parallel.
You do whichever one you can first, and then do the rest of them. We did parallel first and then series,
Yeah.
because that's what we had.
Can you show us one that's kind of the opposite way?
Okay.